What if I told you that the future of computing might look more like the playgrounds of our childhood than the sleek digital world we're accustomed to? Imagine a world where computers operate not with discrete 0s and 1es, but with the continuous flow of analog signals. It might sound like a step back in time, but it could be the next big leap forward in technology. In this video, we're diving deep into the realm of analog computing, exploring why it's making a comeback and how it could shape the future of AI and computers as we know them. So buckle up as we journey through the past, present, and potential future of analog computing. But first, let's rewind a bit and set the stage for our exploration. Analog computing, once the mainstay of early computational endeavors, now stands at the cusp of a revival. In an era dominated by digital technologies, analog computing's resurgence represents a reevaluation of its potential contributions to contemporary challenges, ranging from energy efficiency to computational scalability. This renaissance is not merely nostalgic, but rooted in practical considerations and innovative approaches to computing. To fully appreciate the resurgence of analog computing, one must first understand its historical significance and operational principles. Analog computing predates digital computing and was once the primary method for solving complex mathematical problems in simulations. Early analog computers, such as the differential analyzer developed by Vannevar Bush in the 1930s, used mechanical or electrical components to represent and manipulate continuous variables. The transition from analog to digital computing occurred gradually, driven by advancements in semiconductor technology and the development of digital logic circuits. Digital computers offered greater precision, flexibility, and scalability compared to their analog counterparts. Consequently, analog computing fell out of favor, relegated to specialized applications such as process control and signal processing. However, recent developments in analog computing have reignited interest in its potential advantages, particularly in the context of contemporary challenges such as energy efficiency and computational scalability. One of the key advantages of analog computing is its inherent parallelism and efficiency in handling continuous data. Unlike digital computers, which rely on discrete representations of information, bits, analog computers operate on continuous physical variables, enabling real-time processing and efficient simulation of dynamic systems. The resurgence of analog computing is driven by several factors, including concerns about the environmental impact of energy-intensive digital technologies, the limitations of Moore's law, and the growing demand for efficient and scalable computing solutions. In this context, analog computing offers a promising alternative that leverages the physics of analog circuits to achieve efficient and scalable computation. One area where analog computing shows particular promise is in the field of artificial intelligence, AI, and machine learning. Traditional digital AI algorithms, such as deep neural networks, are computationally intensive and require large amounts of energy for training and inference. Analog computing offers a more energy-efficient alternative by exploiting the parallelism inherent in analog circuits to accelerate AI computations while minimizing energy consumption. For example, companies like Mythic and Espinity are developing analog computing chips specifically designed for AI applications. These chips leverage the efficiency of analog computation to accelerate tasks such as image recognition, natural language processing, and sensor data processing. By offloading computationally intensive AI tasks to analog hardware, these companies aim to reduce the energy consumption and cost of AI inference, making AI more accessible and sustainable. Another area where analog computing shows considerable promise is in the optimization of complex systems and simulations. Unlike traditional digital computers, analog computers excel at solving differential equations and simulating dynamic systems, making them particularly well suited for applications such as weather modeling, fluid dynamics, and various optimization problems. These systems often require solving highly nonlinear differential equations, which can be computationally intensive for digital computers. By harnessing the inherent efficiency and parallelism of analog computation, researchers can tackle these complex problems more effectively and efficiently. Analog computers can process continuous data in real time, offering a level of performance and immediacy that digital systems struggle to match. The practical advantages of analog computing are complemented by a growing appreciation for its historical significance and intellectual appeal. Analog computers represent a unique blend of engineering and physics principles, with roots stretching back to the early days of computing. The fascination with analog computing is not merely nostalgic, it is a rediscovery and reimagining of a technology that predates the digital revolution. Early analog computers, like the differential analyzer developed by Vannevar Bush in the 1930s, showcased the power of mechanical and electrical systems in solving complex mathematical problems. By revisiting these pioneering concepts, researchers and engineers are tapping into a rich vein of computational history and innovation, seeking to combine the best aspects of analog and digital methodologies. One of the significant challenges facing the resurgence of analog computing is the need for greater integration and interoperability with existing digital systems. While analog computing offers numerous advantages, it also presents unique technical challenges such as signal conditioning, noise reduction, and interface compatibility. These challenges require sophisticated solutions to ensure that analog systems can communicate effectively with digital infrastructure. Addressing these issues necessitates interdisciplinary collaboration between engineers, physicists, and computer scientists to develop robust and scalable analog computing platforms. Innovations in materials, science, circuit design, and computational theory all play a crucial role in overcoming these hurdles and paving the way for widespread adoption of analog computing. Fortunately, recent advancements in analog hardware design and fabrication have made it easier to develop and deploy analog computing solutions. Companies like Anabrid and Analog Devices are at the forefront of this renaissance, offering a range of analog computing platforms and tools that simplify the design and implementation of analog systems. These platforms provide researchers and engineers with the flexibility and scalability needed to explore the potential of analog computing across a diverse array of applications. By leveraging modern fabrication techniques and integrating advanced materials, these companies are producing analog components that are more reliable, efficient, and easier to use than their predecessors. As the resurgence of analog computing continues to gather momentum, it is essential to recognize the broader societal implications of this trend. Analog computing offers a more sustainable and energy-efficient alternative to traditional digital technologies. Digital systems, particularly those used in large-scale data centers and high-performance computing applications, consume vast amounts of energy and generate significant heat, necessitating extensive cooling systems. In contrast, analog computers can operate with much lower power requirements and produce less heat, making them a key enabler of a greener and more resilient computing infrastructure. This energy efficiency is particularly important in the context of global efforts to combat climate change and reduce carbon footprints. Moreover, analog computing's potential extends beyond environmental sustainability. It also holds promise for addressing critical challenges in healthcare, such as real-time monitoring and processing of biomedical signals, and in security, where its speed and efficiency can enhance cryptographic applications. By embracing analog computing, researchers, engineers, and policymakers can work together to develop innovative solutions that address some of the most pressing challenges facing society today. The convergence of analog and digital computing, leveraging the strengths of both paradigms, represents a powerful approach to advancing technology in a manner that is both efficient and sustainable. As we move forward, the continued exploration and integration of analog computing could play a pivotal role in shaping the future of technology and its impact on the world. In conclusion, the resurgence of analog computing represents a paradigm shift in the world of technology. By embracing the continuous nature of analog signals, we can unlock new possibilities for energy-efficient computing and innovative problem-solving. While the road ahead may be paved with challenges, the promise of a more sustainable and efficient future makes the journey worthwhile. If you found this video informative, then don't forget to hit that like button and subscribe to our channel for more amazing content. Until next time, stay curious and keep exploring the wonders of the analog world.